Okay, so in the last lecture we have seen what are the ways to determine the absolute configuration of the molecule, what are the nomenclature systems that are used to describe the absolute configuration and to describe the relative configuration. Okay. Now, in this lecture we will now bring in another topic which is basically based on the relationship between the ligands that are present in a molecule, the relationship between the ligands. Like if you have a carbon and if I have two ligands attached to this carbon, of course, it has to attach to 4 ligands, say X, Y, say P and Q, and if I want to know the relationship between this X and Y. Earlier what we have done the absolute configuration of this. We always concentrated on the stereogenic center. Now, in a departure from that, what we are doing now, we try to see that what is the relationship between the ligands that are present in a molecule, in a 3-dimensional molecule which can exhibit stereochemical attributes. Okay. So, this is little bit different. We are not talking about the stereogenic center, we are talking about the ligands, what is the relationship between the ligands in a molecule. Okay. Now, this X, Y, P, we remove this, we put some groups. Suppose we put a methyl, we take this very simple compound CH2 and CH3. Okay. The pentane. Now, in this pentane, propane, the carbon, this carbon has these 2 hydrogens, and if I want to know the relationship between these 2 hydrogens. Now, if I want to look separately, not from the molecule, if I segregate this hydrogen, take this ligand out of this carbon and take this ligand out of this carbon, they are same, both are hydrogens. Or take this methyl, just look in isolation. Okay, this is methyl, and look in isolation of this group, this is also methyl. So, these 2 groups are same, these are called isomorphic, these are called homomorphic groups, homomorphic groups. Homomorphic groups means groups which are in isolation look the same. They look the same means they have the same constitution. Then they are called homomorphic groups or homomorphic ligands. Like these 2 methyls, they are homomorphic ligands. Like the 2 hydrogens, they are homomorphic ligands. Now, we want to know the relationship between these ligands, and this relationship is what is called topicity. So, relationship between homomorphic ligands, between homomorphic groups or ligands or atoms, whatever, it could be just atoms, that is what is called topicity. What type of relationship? Geometric relationship, or you can say stereochemical relationship between the homomorphic groups or ligands or atoms. Okay. Now, there are different types of relationship that is possible. Okay. One is called, I said this relationship is called topicity. So, whatever the name given to these ligands, set of ligands, will have something in front before topic. Okay. Like homotopic, there are set of ligands which are homotopic. There are set of ligands which are heterotopic. Okay. Homotopic or heterotopic. Now, the name suggests that homotopic means like homomar, I have said earlier, same molecule. So, homotopic means there is no difference between the groups or the ligands or the atoms that we are considering. Okay. First of all, they have to be homomorphic, that means they have to be same, otherwise there is the comparison. See, you cannot compare chlorine with a fluorine, they are different ligands. Okay. We are comparing either 2 chlorines or 2 methyls or 2 hydrogens or 2 fluorines, but out of that you can have various situations where both the, suppose these 2 hydrogens, if I consider these 2 hydrogens can be homotopic or heterotopic depending on the structure of the molecule. Okay. Now, structure of the molecule and the way to determine whether they are homotopic or heterotopic. Heterotopic means they are now starting to deviate, they are differentiate, they can be differentiated. Okay. How to do that? There are 2 ways. You can consider symmetry elements to decide the topicity of ligands, or you can consider what is called substitution addition criteria. The substitution addition criteria is the more appealing one, the easier one. Okay. So, what it says that if you want to know what is the relationship between these 2 hydrogens, so you replace one of the hydrogen with a group X and then keep the molecule in the other groups stay there. Okay. So, you get this compound. On the other hand, if you replace the other hydrogen, suppose carbon with X, so you get this compound. Now, you are asked what is the relationship between these 2 compounds, are they same, are they stereoisomers or are they constitutional isomers or whatever. So, try to find the relationship between these 2. Now, they are actually same, because there is, first of all, their constitution is same and there is no question of stereoisomerism here, because there is no stereogenic center, because this is attached to 2 methyl same ligand. To have stereoisomerism, you should have stereogenic center. Interchange of groups does not lead to any stereoisomer. So, they are same. So, if they are same, then that will be called homotopic. Okay. I think it is clear, that will be called homotopic. In symmetry terms, to find the homotopic, you have to find whether there is a C axis present here or not. Okay. Like this molecule has a C2 axis, like if you put an axis like this and then rotate it by 180, this hydrogen will be there, that hydrogen comes here, methyl goes down, this methyl goes up, but it remains the same. So, it has got a C axis, that means the proper axis, the proper element of symmetry, if that is present, then also you can say that they are homotopic. So, you can do 2 things, either you do this replacement of groups, that means that is called substitution addition method, or you can check whether what type of symmetry elements this possesses. If it possesses a C2, then these 2 ligands are homotopic. Okay. Similarly, you can say that these 2 methyls are also homotopic. You can do the same substitution addition thing and you can arrive at the same conclusion, okay, between the 2 methyls. Now, this is homotopic. How do we arrive at heterotopic ligands? Suppose I put a here CH2 CH3. So, this is now I just increase the carbon by 1. So, CH3 then CH2 then CH2 then CH3 and I ask what is the relationship between these 2 hydrogens. Okay. So, what you do? You again do the same substitution addition criteria. So, I substitute the left hydrogen by X. I get this, I substitute now the right hydrogen by X. So, I will get this CH2 CH3 and this is CH3. Now, find out the relationship between these 2. So, what is the relationship between these two? You can tell they are mirror images of each other. They are enantiomers now. Okay. So, these two hydrogens are not the same now. Earlier in homotopic system, they are leading to the same compound. Here there is a difference. Okay. So, this difference tells you, difference means they are now leading to enantiomers, not only stereoisomers, but enantiomers. So, these two hydrogens will be called not only heterotopic, but they will be called enantiotopic. They will be called enantiotopic. Okay. And there is see, it is not necessary always that you consider the ligands attached to the same carbon. You can also do it for different carbons. Suppose if I ask that what is the relationship between these two hydroxy groups. They are homomorphic ligands because they are both OH, constitutionally they are same. So, what is the relationship between these two OHs? So, how do you do? Again apply the addition, that principle, addition, substitution addition principle. So, you put X there, CO2H and CH, keep the other one intact. Okay. So, you get this compound and you replace this one, the bottom one. If you do that, what you end up is OH, H, C, H, X and COOH. Now, what is the relationship between this and that? What is the relationship between this and that? You know that Fischer projection formula can be rotated in plane by 180 degree, that is allowed. So, to know the relationship between this and that, what you do? You rotate this by 180 degree in plane, and if you do that 180 degree in plane rotation, you see this is going to that one or that is coming to this one. That means they are same. So, what is the relationship between these two now? So, they are homotopic, because the definition of homotopic is that this substitution is the substitution addition gives the same compound. Okay. They are giving the same compound. So, these two OHs are homotopic. Now, if you consider that earlier another concept, the symmetry concept, I said if there is a C2, then that becomes homotopic, and you see there is a C2 here. If you rotate it by 180, it comes to the same molecule, it remains the same molecule. So, it has got a C2. So, these are homotopic ligands. So, that is the way to do. Interestingly, if you replace this, change the position of the wedge to this side, then if I ask what is the topicity of these two hydroxy, you see you again do that replacement one, but now you have to, the wedge is on the right. So, you replace the top one by X, the bottom one remains there, and here you replace the bottom one by X, the top one remains there. Okay. Now, you check what is the relationship between these two. Now, you cannot actually interconvert them. See, if you rotate it by 180 degree, it X and OH goes to the left side, but here X and OH are always on the right side. So, what is the relationship between these two? If you put a mirror here now, so this carbon goes to the top carbon, so that becomes top. Best is put the numbering system 1, 2, 3, 4. So, this will be your 4, that will be your 3, that will be your 2, that will be your 1. Okay. So, they are just mirror images of each other. So, you get mirror image systems by this addition, by the substitution addition principle. So, these two OHs are then they are enantiotopic. Okay. And in terms of symmetry elements, I gave you how to do homotopic. Homotopic ligands are connected by C2. Heterotopic ligands, if they are enantiotopic, then they are connected by either sigma, like here you see there is a sigma plane. Here there was earlier there was C2, so that made the two OHs homotopic. Now these OHs are on the same side, so C2 is gone now, but in what is there now is a plane of symmetry. Those are called improper elements of symmetry. So when there are improper elements of symmetry present, the ligands become enantiotopic. Okay, improper elements of symmetry means it could be I, it could be sigma, or it could be S. Okay, and finally there is one more topicity which one should know, and that is again I bring very similar molecules. Sorry, not this one. I create a molecule. Now I actually take the advantage of the wedge formula. Suppose this is OH, this is Cl, and this is H, and then I have a CH2 here and a CH3. So I consider this molecule. That means I have a molecule which already has a built-in chirality here, a stereogenic center with a particular configuration. What is the configuration? You can determine this is your 1, that is your 2, that is your 3, but then you have to check where is the hydrogen, the fourth group, and you can assign the configuration. But I started with a compound with a particular stereochemistry here, okay, and then I am asking what is the relationship between these two hydrogens. Okay, let us try to do the RS configuration if you want. If we try to do the RS configuration, this is, suppose, see, I draw the Fisher projection, this is 1, that is 2, this is 3, this is 4. So in the Fisher projection, I should look through the bonds which are similar. So I look from this side. So this is 4, this is 3, this is 2, and that is 1. 4 is on the horizontal side, so whatever I see, it should be the other way around. So 1, 2, 3 it appears to be clockwise, anti-clockwise, so that should be R configuration. So you have R configuration here. Now what is the relationship between these two? Now among these two hydrogens, see, one will be beta, another will be alpha. Okay. So if you replace this hydrogen by X, by X, or and then put the hydrogen here, keep the hydrogen here and replace this by X. So either replace this by X or replace this by X. What will be the relationship between the two molecules? Now to know that, one basic principle one should learn, and that is the mirror image of R is S. Okay. So when you put a group X here, this becomes a stereogenic center. So it will have a configuration. When I put X here, that will also have a configuration. Suppose by replacing this hydrogen with X, this becomes R, and suppose replacing this hydrogen by X, this becomes S. So basically what I am getting is a RR compound, because this R was already there built in, and here I am getting SR. So what will be the relationship between the two molecules? That I will be generating. See, I can draw this. So that will be X, that will be hydrogen, that will be methyl, and this remains the same, OH, Cl, H, and the other molecule will look like X, then this is hydrogen, this is methyl, and this is C, it remains the same. What is the relationship between these two? These two are now no longer enantiomers, because I said R, mirror image of R is S. So, the mirror image of RR should be SS, but here RR and SR. So, they are now diastereomers, because enantiomers will be RR or SS or SS or RR. So, here substitution elimination is leading, substitution addition, sorry, keep on saying elimination, substitution addition creates two diastereomers. So, these two hydrogens then will be diastereotopic. Will be diastereotopic. Okay. So, basically we have learned topicity is, again to summarize, topicity is basically the relationship, the geometric relationship between two homomorphic ligands in a molecule. There can be different types of topicity. Homotopic systems are connected by C2 axis, number 1, and addition, substitution addition gives the same molecule in homotopic system. In enantiotopic system, the ligands are interconnected by either I or sigma or S, that means an improper element of symmetry is present, and by substitution addition you end up with creating enantiomeric pairs. Okay. So, that becomes enantiotopic. And there is a third scenario where already a stereogenic center with a particular configuration is already present. Then if you are trying to compare two homomorphic ligands, you will see that you end up with diastereomers. So, these ligands become diastereotopic. And in terms of symmetry, because this is a chiral molecule, because you have already a built in chiral center, so there is no question of any element of symmetry present in it. So, basically now we have three scenarios: when C2 is present, ligands become homotopic; when sigma I or S present, the ligands become enantiotopic; when nothing is present, that means the molecule is chiral, then the homomorphic ligands become diastereotopic. What is the utility of knowing this topicity? The utility is that their behavior towards different reagents. Okay. Homotopic ligands behave the same to every reagent, whether the reagent is chiral or achiral. Enantiotopic ligands behave similarly towards achiral reagents, that means reagents which do not have any chirality, and heterotopic and then diastereotopic ligands behave differently all the time, whether it is a chiral reagent or an achiral reagent. There is a spectroscopy called NMR spectroscopy, by which you can differentiate between these ligands. Okay. Diastereotopic ligands always differ in the signal where it comes. Okay. Enantiotopic ligands, unless you add a chiral solvent, they appear in the same region. Okay. And homotopic ligands always come in the same region, same signal, whether it is a chiral solvent or a chiral solvent. Okay. I hope that is clear. So, this is what is the topicity. So, we have now done up to the topicity. Next, what is remaining is how to assign the absolute configuration of these ligands, because these ligands also can be, because to know that which hydrogen I am talking about in a system, I have to assign a configuration, which are called pro systems, pro R or pro S systems, but that we will discuss in the next class. Okay, thank you.